Hi everyone, welcome back to another Pre-Calculus 12 video. We're focusing today on 6.3 Part 1, Special Angles. I'm actually splitting this up into a few videos because I feel like it's a lot all at once. So let's start off with some review from stuff you probably learned a couple of years back but need a refresher on. So let's start off with our special triangles. The special angles to start off with are 30 degrees, 45 degrees, and 60 degrees. And then I'm starting with something that's familiar to you, but I want you to become super comfortable with switching this to radians as well. And remember, to switch to radians, we always, I'm going to make that a bit thinner so it's clear for you to see, we always multiply by pi over 180 degrees. So what I taught you last day was to just think that we're trying to get rid of the degrees. That's why the 180 degrees is at the bottom when converting to radians. So 30 degrees, to think our way through this, would be like saying 30 times pi over 180. So you can see how we're getting pi over 6 is the same thing as 30 degrees. Using that same approach, if I did 45 degrees times pi over 180, we would get pi over 4 is the same thing as 45 degrees. And for 60 degrees times pi over 180, you can see why 60 degrees is the same thing as pi over 3. Now, in my time, I've noticed that a lot of people mix these up. They're tempted to say 60 degrees is pi over 6 and 30 degrees is pi over 3. That doesn't make sense. Let's think our way through this. The larger denominator, so pi over 6, is the smaller angle. So it makes sense that 30 degrees would be pi over 6. The larger degree, 60 degrees, or the larger angle, would have a smaller denominator when you think of pi over 3 in radians. Makes sense logically if you think about this. In a fraction, the greater denominator means you actually have a smaller value. So use that connection to help keep this clear in your mind as we're working our way through this. Again, I'm saying that because this is a common mistake that I see people making. Okay, so let's start off first by looking at 45, 45, 90 triangle. So to start off with, our triangle would be like this and would have a 90-degree angle, where this would be 45 degrees, this would be 45 degrees, and 1, 1, and root 2 are the ratios of the lengths of the sides of our triangle. You have to know those and memorize those, but we can also come up with it by using Pythagorean Theorem. We're just interested in the ratios of the sides compared to one another. So I chose 1 here, but it could be like 10 and 10, and then we would want to do 10 squared plus 10 squared to get the third side squared. That's how we're coming up with this. We're using Pythagorean Theorem. So we chose the number 1 because it's nice and easy. It's the easiest one to work with. So if we did 1 squared plus 1 squared, we would get equals 2 squared, but we just want the a squared plus b squared equals c squared. We want c. That's the reason we get the root 2 up there. So yeah, we're memorizing it, but you can actually derive it and come up with where it comes from. Okay, so then the other way that you could view this, or the way that I want you to think of exactly the same thing, is 45 degrees, like we said here, is the same thing as pi over 4. So we could do the same triangle and think of it in terms of radians, 1, 1, and root 2. It's obviously going to be the same dimensions, but this is our 45, 45, 90 triangles. It's just the same triangle, but in one scenario I did it in degrees and the other I did it in radians, which maybe would make more sense if I matched the colors up. Sorry everybody, I'm off my game today. I usually do this naturally and I forgot. So There you go. There's the first of the two special triangles. To look at the second special triangle, I'm going to show you like a little step along the way. If we were to draw out an equilateral triangle where all of the sides are the same, all of the angles are the same, we could take that and split it in half and put a 90-degree box there. If I were to make it equilateral, I know I'm going to be cutting it in half, so I could do 1, 1, and 1 for the sides, but I don't want to. I'm going to be cutting it in half, so I know I'm going to do 2, 2, and 2, because I don't want to deal with a fraction when I cut it in half. So I've strategically picked 2, 2, and 2. We know in an equilateral triangle, it's 60 degrees, 60 degrees, and 60 degrees. Or if we're looking at our radians, remember that's like pi over 3, and pi over 3. Okay, but we're not interested in an equilateral triangle. Like our trigonometry and everything we're going to be using is based on having a 90-degree angle in there. So I'm going to take just half of this, and I'm going to move that and slide that over to use that to come up with our other special triangle here. So I'm going to, having troubles. I'm going to draw just the chopped up 1/2 of it. If I've chopped it, that side that was 2 is now 1. That's still 2. And then the third side is 3, but with a root sign on top. We're not going to spend the time to go through how to use Pythagorean Theorem to come up with that. You can practice that on your own if you're interested, but we used Pythagorean Theorem to come up with that third side. And when we look at the angles, this would still be 60 degrees, but the one at the top, we chopped it in half. So that's now a 30-degree angle. Oh boy, I didn't want that. Let's bring it back. 30-degree angle, so that's a 30, 60, 90 triangle. Has the dimensions 1, 2, and root 3. Okay, if we look at that in terms of radians, we'd have the same thing going on. It'd still be 1, 2, 3 with a root sign, but instead of 60 degrees at the bottom, I'd have pi over 3, and instead of 30 degrees at the top, I'd have pi over 6. And I keep that straight by thinking 30 degrees, the smaller angle, means larger denominator. So it's a good trick to use to help make this clear. And then I'm going to put those two in a box and say these are our 30, 60, 90 triangles when we're talking in terms of degrees. Okay, so again, we would not be using calculators for this stuff. So between the quadrantal angles that I just did in the last video and these special angles, that allows us to solve a lot of our trig ratios and to find solutions when we're looking for what it is on a unit circle. So let's use that info to dive into an example of how this would be helpful. If we're looking for the cosine of 60 degrees, for example, okay, so I know that I'm interested in this guy here. What I would suggest is when you write your test or your quiz, draw the special triangles at the top, just so you're not thinking your way through it each and every time. But I would look at this and say, okay, I know that 60 degrees is adjacent over hypotenuse. That we know from SOHCAHTOA. And so I would go to my 60 degrees, which we have right here. And I would think, okay, what's adjacent to that? Well, I can see that it's this 1 here. And the hypotenuse is 2. So cosine of 60 degrees, the answer is 1 over 2. If, for example, we have cosecant of pi over 4, okay, when I go to solve this, I feel like I should have done this in hot pink, and I didn't, so let's do that for this one. Cosecant of pi over 4, first of all, I would think, okay, cosecant is the one that goes with sine. Sorry, I needed some tea. Pi over 4, so in my triangle here, I would look to pi over 4. It really doesn't matter which one I use, it's going to be the same thing. And we know that sine is usually opposite over hypotenuse, so I know this time it's going to be flipped because it's cosecant. So it would be hypotenuse over opposite. So it would be, the hypotenuse there is root 2, and opposite is going to be 1. So the answer is just root 2. So it's basically just getting us to practice or apply how to read our trig ratios off of our special triangles. So you do need to have these memorized and know what the different lengths of the sides would be with respect to one another. So if we have tan of pi over 6, again, I would look for pi over 6, and I find that right here. And I know tangent is opposite over adjacent. I keep doing that. Tan SOHCAHTOA, so opposite over adjacent. So we would go opposite is equal to 1. And adjacent to that this time is root 3. Okay, so this is a good one because it's the first time we've had a radical at the bottom. You could give your answer like this, but a better way of dealing with this is rationalize the denominator by multiplying by root 3 over 3. And so we would get square root of 3 over 3. This is the best way to give our answer. So I do want you to take the extra second to rationalize the denominator, and we would say that that is equal to root 3 over 3. Okay, so there are some straightforward examples of how that can show up, but then we also have some that look like this. Let's say we have the sine of 225 degrees, and we want to figure out what that is equal to. And you don't have calculators for this stuff. You are going to do this without a calculator. And so let's go through some strategies for how to do that. I would say, I should have said this earlier, but you can hit pause, try this on your own and think your way through it. When you're ready for the solution, hit play and you'll see me going through the solution with you. Okay, so sine of 225 degrees. Okay, we're kind of new to this. I think a good way to start to figure things out as well, on our unit circle, we know all the way around would be 360. So my first thing is I want to figure out where this is even, because I want to know if my answer is positive or negative. There's somewhere to start. And then I also want to know which reference angle to use. So I know that down here would be 270, this would be 180. You don't have to write them all down. I'm just doing it so that you can help to think your way through this. So when I look at this, I know that my sine of 225 degrees must be in quadrant, oh God, I just butchered that, in quadrant 3 over here. I'm going to write it outside. Okay, so if I know that it's in quadrant 3, well, I'm going to draw, maybe I didn't really need the unit circle, but I'm going to draw my triangle there and say that's where my theta would be, but I want to know what my reference angle is. So to figure out my reference angle, I would do 225 degrees. So like that's, I'm assuming that's my 225 degrees. Somewhere in there, so I would want to subtract 180 degrees from it. So this is sort of practicing or applying what we learned yesterday. So when I subtract that out, I find that it's actually equal to 45 degrees. Okay, so then I think like, I know that this angle is 45 degrees, and we just went through these special triangles. That one stands out to me because I know that it's from my special triangles. And so there's another thing I want to think my way through here though. I'm thinking of sine, and I know sine is like opposite over hypotenuse, or another way we could think of that is opposite would be y over the r value. So going through this, I know that if that's my theta, my y value is actually going to be negative in that quadrant. And my r value, well, that's never negative. So this is helping me to figure out if my answer is going to be positive or negative, thinking my way through it. So now I know that that middle angle, is 45 degrees. So according to my special triangle, I'm going to go back to this again. the two sides are 1 and 1, and my radius, or my hypotenuse, sorry, would be root 2. So I know that the two sides would be, so that would be -1, and that would be -1, and the r value would be root 2. So when I go to do the sine of this, I would have my y value would be negative, so it would be negative, and I would have 1 because I know that my y value there is -1 over the radius, which would be root 2. If you found that confusing, so that would be our answer, but I would do root times root 2 over root 2 to rationalize the denominator. That would be like saying negative root 2 over 2. That's how I would give my answer. If you found that strategy confusing, I'm going to quickly walk you through another way you could do it. So I'm going to say or. You could use this to do the all students take calculus thing. When we figure out, you do need to go through to figure out which quadrant 225 degrees would be in. When you find that it's in this quadrant, you could say, okay, I know that sine is negative in this quadrant because only in these two quadrants is it positive. So I know that my sine of 225 is going to have a negative answer. And then to figure out what it is, what over what, I could just draw out my special triangle with the 45 degrees top and bottom, and this would be 1, 1, and root 2. And I could say, well, I know sine of 45 degrees is opposite, so 1 over the hypotenuse, which is root 2, and so I would get the same result that way. So take your pick of those two solutions, which one you find easiest to make sense of, and stick with what feels easiest to you. I want you to try this next one, and this is also the last one, on your own. So hit pause in the video, and then when you are ready, hit play again so you can see the solution. Okay, so when working our way through this solution, we know that we're dealing with radians because of 5 pi over 3. So my first thing that I do is I need to get some clarity. Like one full rotation would be 2 pi, but when I look at this, this is a fraction over 3. So in my head, I think, what is 2 pi the same thing as a fraction over 3? So I know that I just need to multiply the 2 pi times 3, because the denominator would have been 1, so I would have multiplied by 3 to get to that. So basically, that's the same thing as 6 pi over 3. 6 pi divided by 3 is 2 pi. So that's how I'm getting this and thinking of this. The reason I'm doing that is to help me to figure out like where I go on the unit circle. Which quadrant am I going to be in? This is helping me to figure that out. Okay, so then I know based on that, that I must be in the fourth quadrant here. The other thing I want to think of is if I'm doing secant, I know that secant is the one that goes with cosine. So I'm going to put that in brackets here because when I do the all students take calculus thing, I know that this is going to give me a positive answer because it's in the fourth quadrant and cosine and secant would be positive there. Okay, so now that we know, I'm going to get rid of all of this stuff, and say, okay, I know that I'm dealing with something that's going on in quadrant 4. So that helps me to wrap my head around like what this is. If it's in quadrant 4, and this part would be 6 pi over 3, then this part that I randomly just drew would be my 5 pi over 3. I want to figure out the difference between them. So I want to get my reference angle, and to do that, I would do 6 pi over 3, so this one that I got here, minus my 5 pi over 3. And when I do that, I end up getting pi over 3. So my reference angle is one of the special angles. I know that pi over 3, pi over 4, and pi over 6 are my special angles. So I could draw it out in this fourth quadrant, or if you find it easier to just sketch out, just to remind you to put it into perspective, this is that equilateral triangle that I had chopped in half. So the bottom angle here would still be our 60 degrees. So that would be our pi over 3. And the top angle is the one that we chopped in half. So that would have been the pi over 6. This was 1, this was 2, and this was the 3 with the root on top. So from this, I want to know what secant of pi over 3 is, because that's coterminal to this 5 pi over 3. Well, cosine is adjacent over hypotenuse, so secant is going to be like saying hypotenuse over adjacent. So if I go to this pi over 3, the hypotenuse, no matter what, is 2, but adjacent to this pi over 3 is this 1 down here. So after all of that, my answer is just equal to 2. And I know it's positive 2 because we know that we're in the fourth quadrant where the x values are positive, and it's the x value that we're dealing with because it is hypotenuse, which is like r over adjacent, which is x. So the y value in this fourth quadrant is negative, but we're not dealing with y value when we're talking about secant. I hope you found that helpful. In the last video, I had asked you to do numbers 1 to 4 in your workbook, and this actually will help you with those same questions. So no new questions to go with it, and I hope that this is